Good morning. Time for the next installment in the light lectures. This is a second look into refraction, and let's just remind you where we were. Refraction is the bending of light or the slowing of light as it enters a new transparent material. Now, when it leaves the transparent material and goes into another material, it's going to bend or speed up. In terms of this bending, if you're going from fast material to a slow material, we're going to bend towards the normal. And if we're going from a slow material into a fast material, we're going to bend away from the normal. And that is actually encapsulated in something called Snell's law. And Snell's law says that the index of refraction, oh my gosh, oh my lord, that's supposed to be an N. The index of refraction in one material times the sine of the angle in that material, measured, that's a 1, measured away from the normal, is equal to the index of refraction in the second material times the sine of the angle in the second material. And this, we're going to use this later on. Today I want to focus on lenses, but we're going to use this later on in our last lecture or so to solve for some interesting things that happen when you have refraction of light. Okay, another thing that we did is we basically talked about lenses. And lenses were structures made of glass or some other transparent material that would bend light, and a structure that had this shape, that was a convex lens, would have the effect of taking parallel rays of light and bending them so that they went through a focus. So the focal point on this lens is determined by putting some parallel rays of light into it and seeing where they focus. This is a converging lens, and that's important because we're going to need to deal with that today. There was another type of lens that we had, and this was the type of a lens where it's thicker on the sides than the middle, and this is a concave lens. And light, parallel rays of light going into a concave lens would diverge away. And actually, they trace back to some focal point that is behind the lens. So there are still focal points associated with concave lenses. It's just that they're not in front of or on the opposite side of the light where you would expect the light from a lens to converge. And I said that this type of lens is a magnifying glass if you've ever used it to start a fire or burn something or harm poor innocent ants. This type of lens is actually very common. Most people who have a vision defect are nearsighted, meaning they can see things well up close but not so well far away. This type of lens corrects nearsightedness. If you're a nearsighted person, you have a prescription that is a negative number. I believe one of my eyes before the LASIK was like -2.5. My mom, before she got laser surgery, had a -6. And she needed glasses to find her glasses, kind of thing. Negative because the focal point is on the opposite side. That means that if you take someone's eyeglasses who is nearsighted, which is, like I said, most of the people who have a vision defect, and you hold them in front of the sun, you cannot start a fire or prosecute ants. And if you think back to the book Lord of the Flies, there's a character in that book named Piggy. And Piggy, they talk about how nearsighted he is. And then later in the novel, Piggy's glasses are used to start a fire. That could not happen. So William Golding was a great author, but not necessarily a good scientist. Also, when you have this kind of glasses, we're going to find out that this makes things look small. When you see somebody who is very nearsighted and you look at their face through their glasses, Okay, so here's their big fat head, and here's their ear, and here's their nose, and here's their cheek, and their lips, and then their chin, and whatnot. When you look through their glasses at their eyes will appear to be very small, and in fact, you will see the side of their head coming by over here. It's moved in from where it would have been. So someone who is nearsighted, if you look at their head through their glasses, it looks like their head does this. I'll find you some pictures. It looks like it's squished in. Now, if you ever see somebody who is farsighted, then when you look at them, their eyes will be magnified and they will look larger. Okay, I'll try to find some nearsighted pictures. But let's do this for realsies, okay? So for realsies, let's figure out what happens when we have an object. And we're going to have the same things we had with the mirrors. Oh, one more thing before we go on. Notice that the convex lens is the converging lens. The convex mirror was the diverging mirror. So it's kind of an opposite thing. Lenses and mirrors are opposite in that regard, mainly because lenses refract or transmit light and mirrors reflect light. So this scooped out concave lens is the diverging lens. The scooped out mirror was the converging mirror. Okay, so here we go. Let's talk about what happens when you have a converging lens. Let's draw ourselves a convex lens here. Okay, and there's going to be focal points, and there's two focal points for a lens, one on either side. They will be equidistant. And let's put an object. I'll start with the candle today, but I'll probably get lazy at some point and move to just an arrow. Okay, so there's the flame of the candle. Now we are going to have ray number 1, ray number 2, and ray number 3. And if you look at your notes or if you go back to the old video, ray number 1 had a particular thing that it did. It starts life parallel to the optical axis. So it's going to go ahead and travel along like this. And I'm going to draw it going into the center of the lens. I realize that there's going to be some refraction that happens on the front surface, and additional refraction happens on the back surface, but we can just pretend that everything happens at the center line of the lens and make our life a little easier. This ray starts life parallel to the optical axis, and then when it refracts, it's going to bend in line with a focal point. Now, which focal point is it going to line up with? Is it going to line up with this focal point and go shooting away, or is it going to line up with this focal point and go shooting down towards the optical axis? And the answer is towards the optical axis, because this is a converging lens. Lenses have two focal points, and you use each one once, but figuring out which one to use first requires a little bit of brain power. So because this is a converging lens, it's going to go this way. And that's going to be ray number 1, which I've been doing in blue. Ray number 2 I've been doing in green, and it's going to start life in line with the focal point. Now, since we've already used this focal point, we have to use this focal point for the line, and we are going to get a line that does that. The ray number 2 starts through a focal point, and then when it turns parallel to the optical axis. Oh, look at this. We've got an actual crossing here. So if your eyes were over here and you were looking through this lens at this object, yeah, you see, lenses work a little different. Oh, that's a great looking eye, isn't it? There we go. That's a better looking eye. So there's your eye, and you're looking through the lens at the object. You're not looking directly at the object. You're looking through the lens. You would pick up this ray and that ray. Those two rays are diverging, and they appear to have come from this point right here, which is an actual convergence, meaning the flame appears to be right here. The base of the candle is always on the optical axis, and so the candle would be inverted. It would be real because the light rays really cross, and I can't tell, but this looks about the same size. We could figure that out later. In fact, I'll show you a mathematical way to figure it out in just a lecture or so. Okay, so this is how to draw a picture of a convex lens with the object way outside the focal point. What would happen if I had a convex lens and I brought the object inside the focal point? This is what we do when we have a magnifying glass. So let's go ahead and put the convex lens here. Let's put the two focal points here and here. And now let's put the object inside of this focal point. I'm going to make the object a little taller here because there we go. All right, so there's our object. And now it's time for ray number 1 and ray number 2. Ray number 1 starts life parallel to the optical axis. And when it gets to the center of the lens, it turns and it goes through the focal point. It turns and goes through this focal point because this is a converging lens, a lens that tends to bring light closer to the optical axis. Ray number 2, which I tend to do in green, is now going to be in line with the focal point. We've already used this focal point, so we're going to be along this line. Maybe I made this arrow a little too tall. I'm going to have to extend my my drawing of my lens. You see, I just drew a representative of the lens, but the lens is going to be this big. It's going to be along this plane. Okay, so I'm just going to go ahead and have it turn up here. By the way, you might say, well, what if I didn't have a big enough lens to do this? You know, ray number 1 and ray number 2 are very specific rays out of a myriad, out of millions of rays going in all directions. And so some of the rays would hit the lens, no matter how big or small the lens is. And they would form an image in exactly the same way that ray number 1 and ray number 2 would indicate. So if this ever happens to you, that you drew a too small a picture of your lens, just go ahead and draw a center line on the lens and have everything happen along the center line. Anyway, now this thing is going to turn and go parallel to the optical axis. And you might say, well, Harmon, how is this converging? Well, this ray of light was ready to go off very far from the optical axis, and the lens managed to turn it parallel. So it brought it in closer, not any closer, but not so far away kind of thing, all right? So now your eye is over here, and it picks up these two rays of light. It sees that they're diverging, and your brain thinks they came from back here. So we need to trace this one backwards, and we need to trace this one backwards, and your poor little brain perceives that these two were together somewhere right about there. Oh my gosh, that's way up here. That means that the tip of the arrow, the image of the tip of the arrow is way up there. And since the base of the arrow is on the optical axis, you're going to see an arrow that is much larger. It's a virtual image, cannot be projected on a piece of paper. It's an optical illusion in some way. And larger and upright. Upright is the other word we would use. These are the 3 words we would use to explain it. So this is a magnifying glass. These are the 2 different ways that you can use a convex lens. What about a concave lens? Well, it turns out that the concave lens only functions in one way. No matter where you put the object, inside or outside the focal point, and there's a focal point here, and there's a focal point equidistant on the other side. No matter where you put the object, the same thing is going to happen. So, lordy, 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 I don't know. Where do you want to put it? Let's put it close. Okay, there's my object right there. So ray number 1 starts life parallel to the optical axis. And when it gets to the middle of the lens, it's going to bend in line with the focal point. Now, it's not going to bend down and go through this focal point because this kind of a lens is a diverging lens. It spreads light away from the optical axis. So it's going to take a line that goes away from this focal point, but it goes this way. All right, it continues away from the lens, but it's along this line that travels away from the focal point. Ray number 2, now that we've used this focal point already, in fact, we could even just kind of cross it out because we've already used it. Ray number 2 begins life in line with the focal point. Guess what? Never makes it there. There's a lens in the way. And when it refracts, it bends parallel to the optical axis. Harmon, how is that? How is that a diverging situation? Well, this ray was headed towards the optical axis. Now we've diverted it so it will never touch the optical axis. So that is diverging. And if your eye is over here and sees these 2 rays of light, your brain will perceive that they came from someplace behind the lens. And let's see where that is. Okay, and then the blue dotted line going backwards on this guy. Oh my. Okay, these 2 dotted lines, these 2 lines seem to converge right just behind the lens, and their point is where the arrow is. The base of the arrow is on the optical axis, and we are looking at an upright virtual and smaller. And no matter where you put this arrow, this exact same thing is going to happen. You're going to see something being smaller behind the lens. Now, I told the third period class about the lens maker's formula. Some of you guys, you know what? Tell you what, I'm going to make that a separate lecture. Let's make this a short lecture today, and we'll pick up and have another lecture on lenses and mirrors together with the lens formula, lens and mirror formula. We'll do that later on. So we'll stick with a 15-minute lesson today, and please come to me with questions that you have in our next class session. All right.